Starting in 3, 2, 1, go.
Hi, I'm Thaddeus Pellegrini.
Hello, I'm Matthew Orehick.
Hi, I'm Brendan Lopez.
Hi, and I'm Brian Singer, and this is our EE432 final project. We did an LNA design and fabrication.
The goal of this project was to design and construct a low noise amplifier for 1.3 gigahertz plus or minus 100 megahertz with a gain of 11 decibels using the Motorola MRF 901 RF transistor. A circuit was constructed with copper tape and an FR4 fiberglass epoxy dielectric board with a copper ground plane. We wanted to minimize the noise of this amplifier, so to accomplish this, source and load matching to a source and load is necessary. The LNA circuit had several important components working together to amplify a high frequency signal. Since the amplifier required active components to boost the signal, a bias circuit was constructed to provide the necessary power. A stub with radial open stubs was implemented using microstrip transmission lines in order to match a load impedance to the transmission line characteristic impedance of 50 ohms to ensure maximum power transfer. Since the RF circuit contained elements that did not have matched impedances, a conjugate matching network was implemented to correct for the mismatch. Next slide, please. The biasing circuit for the device, the biasing circuit for RF devices refers to the DC biasing portion of the circuit, which provides current to the transistor. In our project, the biasing circuit provided 10 milliamps to the collector of the MRF 901 transistor and 10 volts between the collector and the emitter. The bias circuit delivered power to the active component of the LNA device using a 15-volt DC voltage source. We generated the voltage directly using an NI multi-SIM device, although we also experimented by connecting 10 1.5-volt batteries in series with one another. Next slide, please.
To calculate the values of the resistors made, the assumption had to be made that the current going through R1 is equal to 100 times the current going through the base of Q1. The values of the resistors can be calculated using KVL from there. For our resistors, we determined that R1 was equal to 46K, so we used a 47K resistor. R2 was equal to 74K, so we used a 75K resistor. And R3 was equal to 493, so we used a 470 ohm resistor. Next slide.
Sorry, I was unmuted. From there, we had to design the stub length. So what we did was we made two schematics, one straight open stub and one radial open stub. Now, using the straight open stub, we use line calc as we put the frequency was 1.3 gigahertz, and then we put all of the necessary design schematics into here. And we were able to simulate how much the width and the length should be to optimize it for 50 ohms. And this was for the straight open stub. Now, the radial stub, you can't just put into line calc. So we used the tuner method where we would fidget the width and the length to get it the optimized graph, as you can see here in the next slide. So we simulated using the tuner tool here, right in Mr. Stub, and we tried to make it look similar to the straight open. You can see the straight open doesn't have as good as bandwidth. I mean, that's why we use the radial stub. And you can see here it's at 1.3 gigahertz, which is the necessary design schematic.
The bias circuit was constructed about 1.7 inches from the center of the board to make sure that we had enough clearance for the RF isolator system. All of the microstrip lines were made using copper tape with a conductive adhesive and attached to the FR4 fiberglass epoxy dielectric board with the copper ground plane. The physical dimensions of the DC bias circuit were sort of arbitrary since the size and the length are unimportant at low frequencies, but the physical dimensions, they became much more important in the construction of the RF portion of the LNA device. The resistors and the transistor within the DC bias circuit were soldered in place using just, standard lead solder for electronics. A hole was drilled through the board in the center to allow the transistor collector pins to attach to the ground plane, while allowing the base of the emitter pins to connect to the microstrip transmission lines on the top of the board. The base was directed towards the input side of the LNA, while the emitter was directed at the output side at the right-hand side of the board. SMA connectors were soldered to the device to allow RF signals to be input and output. Later on, we constructed a matching network, which it involved a little bit more hardware using this same copper tape. Next slide, please.
After we constructed the circuit, the DC bias circuit, the implementing the transistor, the SMA ports, and the transmission lines and the stubs, we needed to begin testing to see if we are able to obtain the correct gain and loss. So we used a VNA Nano to and the VNA software to upload it to a computer, and an attenuator to connect to the output of the LNA, and we needed to test the S1 parameters so that we could begin testing for our matching network. Next slide. So these are the results we had obtained after using the VNA. The one on the left is the typical input-output of the VNA. We got a gain of 7.7 dB and a return loss of negative 3.4 dB. And on the right is are the results of the circuit, but flipped. We had swapped the output with the input and the input with the output, along with the attenuator. With this, we were able to capture and export these results into MATLAB and compile them to a single data set, and then import them back into ADS, where we could develop the matching network. Next slide.
In order to design our matching networks, we used MATLAB to find the values for gamma S and gamma L. And once we had the gamma S and gamma L value, we were able to use the Smith chart tool in ADS to determine the electrical length of the transmission lines. After we had the transmission lines, we used the line calc tool to determine the physical dimensions of the transmission lines. And then we were able to simulate our circuit with the matching networks in, and our matching network simulated 9.1 dB gain at 1.3 gigahertz. The matching network was not perfect at first, so we used the tuning tool in ADS to make sure that the center frequency was closer to 1.3 gigahertz. Next slide, please.
This is the results after the matching network, and we were unable to get the gain that we were looking for, and we were able to set it up directly as it was in ADS, but the results were not the same. We were getting a gain loss after adding the stubs. Next slide.
So in conclusion, we didn't quite meet the 11 decibel target that we had. This was a result of suboptimal matching network performance. We ended up getting 7.7 decibels, which is still, that's still pretty good gain, especially since this is a low noise amplifier. We met the return loss requirements of 2 to 1. We correctly amplified the center frequency at the bandwidth that we desired using the materials that we wanted to use. But we ran into a few issues, one of them being we ran out of materials towards the end when we were working on our matching stub, so we weren't able to develop it as fully as we wanted to. We had some other hardware issues, such as one member's soldering iron caught on fire, and so that caused a bit of an issue. We also had a bit of a serious injury where one of our members accidentally harpooned himself in the foot with the X-Acto knife, which caused a bit of a delay. But all things considered, we think we had quite a good success. The project went well, and we all learned a lot, and we're happy that we were able to work on this low noise amplifier this semester. Thank you. And if you have any questions, we'll be happy to answer them for you to the extent that we can.